Hi, my name is James, and in this video I will explain a device called an organic light emitting diode, which is more commonly known as an OLED. An OLED is a solid-state organic light emitting diode that emits photons through an electroluminescent layer made of an organic compound. The structure of a basic OLED is shown in this image. The power supply is connected to the cathode and the anode. The cathode is shown by the pink layer way on the top, and the anode is shown by the greenish layer near the bottom. The cathode emits electrons and the anode accepts them. The emissive layer consists of organic molecules that behave like a semiconductor. The organic molecules can be conductive because of the delocalization of pi electrons in its molecular orbitals. Because of the flow of pi electrons in this organic compound, the molecules can have properties just like a semiconductor. Image 1 shows a bilayer OLED, which is currently the most used OLED configuration. As we can see in image 2, electrons, which are represented by the black dots, flow from the cathode towards the emissive layer. These electrons want to occupy the lowest unoccupied molecular orbitals, which is analogous to the conduction band in semiconductors. Likewise, holes, which are the white dots, flow from the anode towards the emissive layer. By taking the highest occupied molecular orbitals along the way, which are analogous to the valence band in semiconductors. Since organic compounds cannot be simply p or n doped like regular semiconductors, a conductive or transport layer is needed to transport holes from the anode to the organic material layer to help the flow of carriers. Lastly, in organic molecules, holes travel faster than electrons. Therefore, the recombination occurs closer to the emissive layer near the cathode, and a photon is given off in the process, which is shown in step 4. Depending on the energy difference of the highest occupied orbital containing the hole and the lowest unoccupied orbital containing the electron, recombination of the two charged particles will emit a photon of varying wavelengths. This is similar to different photons emitted by different sized band gaps in semiconductor devices. Different colors can be achieved by adjusting the material based on its properties and energy differences in the molecular orbitals, just like semiconductors. White light is achieved by either stacking multiple OLEDs or putting red, green, and blue OLEDs very close to each other and lighting them all at once. Although the latter method is less efficient, it is easier and more widely used. Although the bilayer OLED is the most widely fabricated configuration, there are different variations of the OLED with varying layers. When the OLED was first tested in 1965, there was only a single emissive layer between the cathode and the anode. From there, a whole transport layer was added right on top of the anode, and the emitter also doubled as an electron transport layer, which would later be separated into two distinct layers. In further attempts to increase the efficiency in radiative recombination, a hole blocking layer was added to try and increase the recombination rate in the emissive layer. These heterojunction OLEDs are the latest attempts in making OLEDs as efficient as possible. In this slide, we can see a more band diagram-like representation of the different multi-layer configurations. Each layer is added to try and get the rate of recombination of the electron-hole pair as high as possible in the emitter layer. There are two types of materials that can be used during OLED fabrication. The first type results in small molecule OLEDs, which use smaller molecules for the organic layer. Evaporation deposition is commonly used to deposit the organic material onto the emissive layer on the OLED. The second type, being polymer LEDs, use larger molecule solutions to fabricate the organic layer. The solubility of the polymer allows easier coverage of larger areas and the ability to be printed. However, because of its water solubility, it cannot be layered well with other layers. Small molecule LEDs are more widely used because of its accuracy and controllability, but is much more expensive. There has been some recent research to try and make small molecule LEDs through solutions instead of evaporation deposition to lower the costs. There are many options in configurations when fabricating and using OLEDs. Passive matrix OLEDs, which you can see by the image on the left, have strips of cathodes and anodes that intersect in a grid light format. The LEDs light up based on the coordinates of the grid and which cathode and which anode strips are activated. However, this is inefficient and only practical in small-sized matrices. For larger LED displays, active matrix OLEDs are used, which can be seen on the image on the right. In the active matrix, the cathode and the anode both cover the whole area of the LED grid. However, a thin film transistor array is placed in every grid coordinate between the emissive layer and the anode to control the individual lights on the grid. Regular OLEDs usually have a reflective, low work function metal as a cathode and a stable transparent anode, such as indium tin oxide. This creates a top-emitting LED shown on the figure on the top left. However, the cathode can also be replaced by a transparent conductive material to make the entire LED transparent. Furthermore, the cathode, anode, and substrate can all be swapped with a flexible material to make the LED flexible and foldable. Although the electroluminescent property of organic materials was discovered much earlier, Ching Tang and Stephen Van Slyke fabricated the first OLED diode in 1987. Over the years, the OLED technology has been expanded to a wide range of color spectrums and has made its way into the consumer market. Because of its small size, lightweight, and ability to emit bright colors, it is predominantly used to make screens, such as televisions and cell phones. Furthermore, OLEDs are slowly making its way into the solid-state lighting market, but currently regular LEDs perform much more efficiently at a lower cost. The biggest obstacles in development has been sealing the OLEDs and preventing degradation, as well as its high manufacturing costs. OLED technology has many benefits over regular LEDs and other types of non-solid-state lighting. OLEDs are not restricted to the typical 3-5 substrates as regular LEDs and can be formed on a variety of substrates with varying desired properties. Because of this, it is more adaptable, lighter, and smaller compared to regular solid-state LEDs. On top of its size, OLEDs also consume less power and have faster response times. With its many benefits, it makes you think why regular LEDs are not yet obsolete. This is mainly because of the very high costs in fabricating OLEDs. All parts of the OLEDs are extremely sensitive to environmental conditions during and after fabrication. Therefore, it is not uncommon for OLEDs to degrade in luminance over time and use. The degradation of OLEDs can also occur at different rates for different colors and can cause colors to look skewed over time.